So in the second half of section 11.4, we look more closely at linear approximations and particularly the increment of variables z and x and y and the differentials of x, y, and z as well. So this concept will help us to define differentiability of a function of two variables, and it'll give us a better idea of how to use these approximations, and it'll also allow us to put bounds on errors for these approximations as well. And we'll see at least one application problem that deals with something similar to that. Okay, so we just have to remember that if AB is a point in the domain of a function f, then a plus delta x is the increment of away from a. So in other words, it's a delta x distance away from a. Okay, so we'll talk about that delta x as the increment in x. Similarly, b plus delta y is the increment of y away from b. Okay, z will have something similar, but x and y now are independent variables. So these are easy to define. Since z depends on f of x, y, its increment is a little bit more particular. We have to involve the function f of a plus delta x, comma b plus delta y. So in other words, the increment in z, if we move from the point AB, is given by evaluating the function at a plus delta x and b plus delta y. So we've moved away from a and b by delta x and delta y respectively. What is the difference in our function? What is the increment in our function? That's what delta z is called. Okay, now we use that definition in the beginning part of this sentence to state that f is differentiable at a point AB if the increment of z can be written in this form. So let's break that form apart. This is partial of f with respect to x at AB times delta x plus partial of f with respect to y at AB times delta y, and then plus epsilon 1 times delta x, epsilon 2 times delta y. And these are essentially what we used to have in Calc 1 was that these derivatives are easily defined in terms of a single variable, and we would just look at the limit delta y over delta x as the change in x went to 0. And if that limit were to exist, we saw it as the difference quotient very often. If that limit exists, we said that the function f was differentiable. Well, that was because we only had one variable to increment, delta x. So this expression is much easier to write and uses your definition of f at a point a, or at x value a. Now we have two free increments. We can change delta x and we can change delta y. So this definition needs to be broken apart because we don't have a common denominator anymore. We might think about this in parts, loosely speaking, as increments in certain directions. In other words, in the x component, delta z over delta x can be written as, well, f sub x of ab plus epsilon 1. So, and that's essentially, it just looks like we're solving for things involving x. On one side, we're collecting delta z over delta x for what we see down below. Similarly, in the y component, we have delta z over delta y, and that, loosely speaking, just in the y component, that's the contribution of delta y to delta z. And we have, well, the derivative of f with respect to y, or z with respect to y in that case, plus some epsilon. Now, as delta y goes to 0 here, this epsilon 2 should go to 0. So both of these are running to 0, as well as this. Okay, and same thing for x. As delta x goes to 0, epsilon 1 should be going to 0. This is all written down here. And again, this distance is shrinking, as are these. Okay, so if those limits exist down here, as such, everything goes to 0 basically, then we know that this is the well-defined differential delta z. Okay, again, it's a tough thing to put together how it relates to our one-dimensional case, But the idea is that we're going to shrink our increments, and delta x and delta y are free variables, right, compared to just delta x and single variable calculus. And as that happens, our derivative essentially pops out of this, and the function is differentiable if that limit exists. Okay, knowing the details of this much more fully than that, and even if that sounds cloudy, it's okay. We don't need that practically. Okay, so just know that we can't just write down a difference quotient to come up with this differentiability statement for z. We have to put it together like this because we have different denominators, delta x and delta y. So this is how it all splits apart. Luckily, we have a nice theorem to accompany this thing. If the partial derivatives fx and fy near AB are continuous at AB, then f is differentiable at AB. So that's good. And we can see that that really kind of relies on this, right? If you know, these partials need to exist, and moreover, if they're continuous, then we know that this, as well as these limits, is going to exist. So we'll just rely on that as the fact or the characterization for differentiability of a function f in terms of this general ordinary differentiability versus partial differentiability, which was section 11.3. Now, differentials come into play here. And that, of course, we just spoke about the increment of x and differentiability of increment of z and the differentiability of z. And again, let's consider this function z equals f of xy in terms of differentials. Dx and dy now are independent. In Calc 1, it was very common for us to set dx equal to delta x. It's an independent variable. We get to choose the change in x that we want to address. However, dy was more complicated. Dy, what we often saw as f prime of x dx. And that actually should look just a little bit familiar. F prime of x, if we substitute this for delta x, it's starting to look like what we saw on the previous page, the derivative of f times delta x. It matches this situation for another analog to what we used to be able to do. Okay, so now both dx and dy are independent variables, so we're really playing this game with z, right? So that y should really be a z in here, and we're seeing something along these lines. Okay, but there are two variables, so dz we need to also input y's contribution to this situation. Okay, so just roughly sketching things above there, let's clear that out to not confuse the issue anymore. The total differential dz, this is a dependent variable on dx and dy and the function f overall. So we define it as partial of f with respect to xy dx plus partial f with respect to y of xy dy. And while we're rewriting that, just using z in place of f, we can have the same over here. Notice we have partial derivatives in this with ordinary differentials. Partial derivatives and then ordinary differentials. Okay, that is our differential dz. It has to break into components because now it depends on two different independent variables, x and y. And that's the way we'll express it. We might sometimes write dz as df, make a note of that for the future. So, like we would do in Calc 1, as I've already sort of pointed out, loosely speaking at least, since dx is an independent variable, we'll take it to be delta x as we choose. Independent variables give us our leeway, or gives us our freedom of choice to select what value we want them to be. So we could choose that to be delta x, since x minus a, something similar for dy. Okay, what that does is it converts with this choice, it converts dz into this expression, f sub x of ab, partial of f with respect to x times x minus a, partial of f with respect to y times y minus b. And what we're starting to put together here on the right, it looks like most of the equation for linear approximation of a function f of xy, that L function we calculated in the first video of this section. So we look down here, we see the full thing written out. All we have to do in this situation is we'll realize that f of xy is approximately, for xy near the point AB, so So for an xy that's near this point AB, the value of the function f of xy is approximately what the value was at AB plus dz. And dz, with those choices we made above, is equal to this. And that's exactly, well, with f, the partial is evaluated at AB, but this is exactly dz at the point AB. Okay, so essentially it's our error, it's our distance off, or it's our change or increment in z away from the point AB. And these things are approximate. We'll see that these are approximate because there's no limiting process involved here. Again, we fixed dz, we chose dx not to be infinitesimally small anymore, and we've chosen dy not to be infinitesimally small anymore. We haven't taken the limits in what we have down here. So this is still just an approximation of these things. Okay, but again, that's the whole point of a linear approximation. So, and then just further clarification along those lines, we see that, yeah, we're noting that delta z is the actual change. That's important to realize of the function z equals f of xy as x and y move away from AB. And dz is an approximation of the change in z equals f of xy near AB. So in some sense, it does give us, it could give us some approximation of error in an approximation. Okay, if the closer we are to AB, in other words, the smaller delta x and delta y become, or dx and dy become, limiting dx and dy to be infinitesimally small, we get that delta z is approximately close to dz. In the limiting process, those two things are actually equal, or they become one another in these derivatives. Okay, again, that's a lot of theoretical background. We don't need all of that to be able to do the problems in this section. So let's look at something more tangible for a moment. Okay, find the total differential of the function z equals x squared minus xy plus 3y squared. Compare dz to delta z if xy changes from 3, -1 to 2.9, -0.9. Okay, so we need to recognize what we're looking for and what we've got. They want us to find the total differential. This is the total differential from the formula on the previous page. So write that down to give us a clue as to where we need to head. Our function, f of xy, has been given as such. Partial with respect to x, partial with respect to y, gives us these two values. We can input both of these here and here in this general form. And what we get is below, and that is our total differential of z. It's a pretty easy process. Again, loosely understanding what we're doing here should be sufficient for the purposes of this section and this chapter, really. Okay, so dz has been found, our total differential is settled. Now, the next thing they ask us is to calculate dz as 3, -1 moves to 2.9, -0.9, and calculate delta z as 3, -1 is moved to the other point of 2.9, -0.9. Okay, those are different things, remember? Delta z is the actual error, the actual increment or change in z, and dz is an approximate error based on the distance between these 2 points, the delta x and the delta z, okay? In terms of how we've defined it on the previous page, or decided to use it in linear approximations on the previous page. So for the differential dz, changing from this point to that, we notice that dx, again, we'll select dx to be delta x here. And then once we have that, we're changing from 3 to 2.9 in the x component. So we do the end result, 2.9 minus the start. So that's 2.9 minus 3 to get -0.1. Similarly for dy, it's delta y, and changing to -0.9 will subtract the -1 we have in the first point's y component, and we get 0.1 out of this. Okay, so now we know our values for dx and dy. If we look at our total differential formula from above, we're implementing this formula when we write this down. Okay, so that's 2 times this x value of 3 minus this y value of -1 times this dx value of -0.1. Okay, it's implementing the formula as we see it, plugging all these numbers in. When we're done plugging all of that in, simplifying our result, we've got dz is equal to -1.6. So that's our differential at the point 3, -1, as that point changes to 2.9 to -0.9. Now for the increment of z, remember the increment is the actual difference. So the increment is fairly straightforward. We just take f at the point that we end up at, subtract from it f at the point we started at. This is our function, f of xy. It's, again, x squared minus xy, so x squared minus x times y plus 3 times y squared. Okay, 3 times y squared at the end there. And taking those two differences, evaluating this function at both of those points here, and then the evaluation at the other point is this. And then the difference of those two, we end up with delta z being equal to -1.55. All right, so we see that dz and delta z are close in value. In another, again, we're going to note that we didn't move very far away from the point 3, -1 when we came up with this calculation. We went from 3, -1 to 2.9, -0.9. We only moved by increments of -0.1 and 0.1. So dz, which represents the increment along the plane, is very close to delta z, which is the increment along the actual surface. Okay, so part of the utility of dz, in this problem it's not so clear, but it's typically easier to calculate the increment in dz because it's a linearized function, right? Though it's not as accurate as what you would get for the actual change, there's a little bit more work to plug these all in. Since this was a polynomial function to begin with, this function f up here at the top, the point's not proven as well as it would be if this f of xy involved cosine or natural log or e to the x, exponential functions. Anything more complicated than a polynomial could convince us that we'd much rather deal with dz than delta z when it's an option. Okay, so that is comparing dz, the differential of z, to the increment delta z. And of course, as usual, we have a 3-dimensional version of this, or we have a function of 3 variables version of this. And we talk about the increment of w, delta w, and it's exactly equal to this. And the total, very analogous, or completely analogous to the 2-dimensional situation. The differential dw is very similar to the differential dz, or the total differential dz, only now z being an independent variable, it's thrown onto the list on the right, and dw is now the dependent differential in this situation, dependent variable. Okay, again, the functions of 3 variables are kind of sort of the big brother that gets a little bit ignored in a lot of the original talk about these functions, about these concepts and principles in this chapter and probably throughout the course, because it's hard to draw a function or imagine what the graph of a function w equals f of x, y, z looks like, because we have 4 variables in this. That's a 4-dimensional space. We don't live in a 4-dimensional space, and it's really hard to fathom what one looks like. All we can ever imagine is what slices, 3-dimensional slices of a 4-dimensional space might look like. So if our treatment of these larger variable situations is a little bit more brief, it's because of that. But again, if you can see it in 2 dimensions and use these things in 2 dimensions, then they just extend simply to 3 dimensions, usually by just the addition of a z component. So that's always kind of nice. All right, so one more example, and that involves a function of more than 2 variables. This is a nice problem. We're told that the dimensions of a rectangular box are to be 20 centimeters by 40 centimeters by 50 centimeters. Okay, and each measurement is correct to within 0.1 centimeter. So we know there's some margin of error. So our error bounds for each of these length measurements is 0.1 centimeter. They ask us to use differentials to estimate the largest possible error when the volume of the box is calculated from these measurements. So that's dz, not delta z. Delta z would be the actual largest possible error. And that would be doing something like 20.1 times 40.1 times 50.1 minus 20 times 40 times 50, saying that all the errors, all the lengths were off by a full 0.1 amount, and the difference between the box's actual volume and the calculated volume is that much. dz is a little bit more simple to do. We take the volume of a sphere, v equals x, y, z. So v is a function of the three variables x, y, and z. Okay, and we know that each of our errors are less than or equal to 0.1. So that's either 0.1 less or 0.1 more. So the absolute value of each of our differentials, dx, dy, dz, is less than or equal to 0.1. So really, in the background, we realize that dx, we might say, for instance, is greater than or equal to negative 0.1. It's no more an under calculation than 0.1. It's no more an over calculation than 0.1 as well, in terms of an over measurement or whatever it is, however we came up with those numbers. So we just leave those as absolute value and the note at the beginning, and then how we act from here will be pretty straightforward. We'll kind of drop that, and I'll introduce it, or I'll mention it at the very end of the problem. We know our dimensions are as follows, given by the problem. And then we know that we're dealing with differentials. So we're going to need to talk about the total differential dv. And that's what's motivated the work that we have here. We need the partial of v with respect to x. We need the partial of v with respect to y. And similarly for z. For all three of our variables, independent variables in this, we come up with our partial derivatives. Okay, that goes into our total differential expression for dv. And at this point, it's kind of a nice thing to just fill in what we know. We know that the point we're interested in is a box that we believe or have measured the dimensions of to be 20, 40, and 50, but there is some error. So that's what the dz, dx, dy, dx are all covering. Okay, when we plug at yz in front of dx, we get, this is 40 times 50, and that's 2,000, and the other two are calculated similarly. So now we're at this expression with numerical values in place of the variables. And the last thing we need to recall is that all of our differentials are bounded above by 0.1. They're also bounded below by negative 0.1, but we could check either one and take the larger two of the errors. We're going to find that the greater one is going to be the one that makes, actually they're all going to be the same. It would be plus or minus whatever this number is in the very end. But it suffices for us, since we're dealing with positive measurements here, to just deal with positive error and say that's the most off it's going to be. Okay, so here's where we stated that. So we know that dv, which is equal to this, each of these is less than or equal to 0.1. So we've written that out off to the right. We could also say, on the other hand, addressing that plus or minus the absolute value situation a little bit more directly, we could also say off to the left that dv is greater than or equal to the same things, 800 times negative 0.1, and so on, right? For the other three, for the y and then the x to follow that on the left. It's going to come out to plus or minus anyway, so it really doesn't matter. Another thing we might have been able to do is to just leave these as absolute values and then just see this positive 0.1. Anyway, just a little bit of quick reasoning when we get to the end of this problem convinces us that we're okay with what we did. That's 0.1 times each of those coefficients above. And dv then is less than or equal to 380. This is centimeters cubed. All of our measurements were in centimeters. Units were pretty easy to deal with. We'll reintroduce them in the end because we can. And so then we conclude that the largest possible error in calculating the volume of this box was either over 380 centimeters cubed or under 380 centimeters cubed. So that is one nice use of differentials to talk about approximating errors in measurement or calculation. So that should wrap it up for section 11.4. Again, if you know how to do the problems, it's a little bit more important then understanding exactly what's going on in terms of the pictures, denoting dz or dw, the differentials, and realizing that that's the increment in the plane, the approximating plane or the linear approximation, versus delta z or delta y, which is the actual increment along a surface, or the 3D analog of a surface for w. That's the main difference. dz is the change along the plane. Delta z is the change along the surface. And from there, the rest is just details and formulas. So good luck with these problems.